In the previous video, we have used the idea of direct sum orientation to define the orientation on the boundary. Recall that given a manifold M with boundary and an orientation on M, we define the induced orientation on its boundary as follows. This orientation is going to be represented by ordered basis V1, Vm-1, such that the following represents the orientation on M. We recall here NP denotes the outward normal vector at P. Recall that we had this example here where the orientation on M is the counterclockwise orientation, right? So then from that we can deduce that the orientation on the boundary circle must be in this direction. So it's also counterclockwise. And that's quite intuitive. Now let's look at another example. Let's look at the example of a homotopy space. Here we let M be some manifold with boundary, and we define the homotopy space on M to just be the space, the interval times M. Now let's say we have some orientation on M, and then on the interval 0 to 1, we just take the standard orientation. So the one represented by the vector pointing this way. From our previous discussion, this induces a product orientation on this homotopy space. Let's call the space X. Our question now is, what is the orientation on the boundary of X? Well, first, let's recall what the boundary of X is. Recall that the boundary of X is just the union of this copy of M with this copy of M. Now, let's figure out what the boundary orientation is. Our claim is that the boundary orientation on this M0 is going to be opposite to the orientation on M, whereas the boundary orientation on M1 is actually going to be the same as the boundary orientation on M. So let's see why. Let's first take a point P on M0 and we'll try to figure out the boundary orientation at P. We'll do so using this definition. Thus, the first step is to take an outward pointing normal vector at P. Next, to figure out this boundary orientation, we need to know the orientation on X. And recall that the orientation on X is the product orientation. To see this explicitly, let's just take an example. Let's say that M is the closed unit disk, and let's put the counterclockwise orientation on M. Now, this argument will actually work for any manifold in general, but it's just easier if we have some concrete example. So don't worry that we assume too much about M. It's just easier to draw that way. Okay, so now let's see what is the product orientation on X. Now on M, a counterclockwise orientation could be represented by these order bases E1, E2. So that means that the product orientation on X could be represented by these minus NP, right, corresponding to the orientation on the unit interval, and comma E1, comma E2. In this order. So we have to define this boundary orientation in such a way that it's going to be equal to this orientation. In other words, whichever vector we put in here, should it give us a triple that is equivalent to this triple. We claim that therefore the orientation on this tangent space here must be opposite of that on M. In other words, here a vector of an ordered basis representing this could be E2, E1. So let's see why. First, since this vector, this triple, represents the orientation on X, we know that this order number is 1. But by definition of product orientation, this order number is just the product of this order number, and this order number is minus 1. So that means that this order number is also minus 1. So that means that the orientation on the boundary here is not represented by E1, E2. So in other words, E1, E2 represents the opposite orientation. Thus, the boundary orientation on M0 is opposite to that of M. Now here, we wrote a lengthy algebraic calculation, but we can also just think intuitively. Here what happened is that we want these two ordered bases, right, to be equivalent. Now, this and this represents opposite orientation, so therefore this and this must also represent opposite orientation. Now what changes when we look at this piece, this copy of M instead? Well, the difference here is that the unit normal vector, the outward pointing unit normal vector at Q here, is actually in the same direction as this orientation on the unit interval. In particular, at Q, the orientation on the tangent space of X is given by NQ E1, E2. That means that the boundary orientation should be E1, E2. So this copy M1 here has the same orientation as M. So to remind us of the fact that M0 has opposite orientation as M and M1 has the same orientation as M, we will often write things this way. We'll say that the boundary of X is M1 minus M0. So this is an oriented version of the boundary. Alright, so that's the boundary of a homotopy space. The last induced orientation that we need to discuss is the preimage orientation.